Hello, my name is Shahriari, and this is a lecture in a series of lectures on undergraduate abstract algebra based on my book, Algebra in Action, a course in groups, rings, and fields. The subject of this lecture is the general linear group and the special linear group and their sizes in the case where F is a field of order P. I'm going to tell you what a general linear group is. I'm going to tell you what a special linear group is. Then we will talk about the size of the general linear group in the case where the entries are from a field of order P, and the same with the special linear group. Along the way, I will talk about n by n matrices as an algebra and GL and R and a little bit about fields, the general linear group and the special linear group. So let's start with n by n matrices. One notation for n by n matrices is R to n times n, or M for matrices n by n over R. So these are n by n matrices where the entries, the things that go in the matrix, are real numbers. What are the games we can play with matrices? We can add two n by n matrices and get another n by n matrix. We can multiply two n by n matrices and get another n by n matrix. And we can multiply an n by n matrix by a scalar. If we just focus on addition, then n by n matrices with addition is a commutative group. What does that mean? That means we have closure. The sum of two matrices is also an n by n matrix. We have associativity. A plus B plus C equals A plus B plus C. We have an identity, the zero matrix, the matrix that has all zeros in it. If you add that to any matrix, nothing happens. And every matrix has an inverse, minus A, that if you add to A, you will get the zero matrix. Note that when we say the inverse in this context, we don't mean the matrix inverse, because we're now only focusing on addition. The inverse is the thing that when you do the operation with the matrix, you get the identity. The identity here is the zero matrix. So the inverse will be minus A. A plus B is also B plus A. So this makes it a commutative group. If you look at multiplication of matrices, then you don't have a group. We do have closure. If you multiply two n by n matrices, you get an n by n matrix. You have associativity and you have an identity, the identity matrix. But not every element has an inverse. In this case, the inverse of a matrix would be another matrix that if you multiply it by it, you get identity. All of these properties of matrices are proved in my videos on linear algebra. I do urge you to look at those if you're not familiar with n by n matrices. With matrix addition and multiplication, if you just look at addition and multiplication together, then we have what's called a ring with identity, a non-commutative ring with identity. It doesn't matter if you know what that is or not. When we get to the ring theory lectures, we will go into that. If you look at n by n matrices with addition and scalar multiplication, then you have a vector space. And you can look at my linear algebra videos for an explanation. An object that's a ring as well as a vector space is called an algebra. And n by n matrices give us an example of an algebra. The key for us is that with matrix multiplication, we don't have a group. But if we just focus on invertible matrices, if you don't look at all n by n matrices, but the ones that have a inverse, then they do form a group called the general linear group, GLNR. The N tells us that it's n by n matrices. The R says that the entries are real numbers. This is the group of units of n by n matrices. When you look at multiplication, you don't get a group, but if you throw away all the elements that don't have inverses, then you do get a group. What's GLNR is the group of invertible n by n matrices. An invertible matrix is a matrix that there's some other matrix that you can multiply by and get the identity matrix, the matrix with ones down the diagonal and zeros elsewhere. The entries are real numbers. GLNR with matrix multiplication is a group. It's one of the examples we can think about when we're thinking about group theory. What does that mean to say that it's a group? If we have two invertible matrices, then the product will also be in GLNR. That actually needs a little proof, because we know that if you take two n by n matrices, you multiply them, you get an n by n matrix, but we have to be careful and make sure that if you multiply two invertible n by n matrices, you get an invertible one. And the reason is that we can write down what the inverse of AB is. The inverse of AB is B inverse A inverse. Why is that? Well, if you take B inverse A inverse times AB, you will get the identity matrix. This is an example of the socks and shoes theorem. If you put on your socks and then shoes, when you take them off, you've got to take off your shoes first, then your socks. So we have closure. We also have associativity. AB times C is the same as A times BC. This needs actually a proof, and I have a proof in my linear algebra videos that matrix multiplication is associative, is something that we use quite often. We have an identity matrix, the n by n matrix that has ones down the main diagonal and zeros everywhere else. That has the property that when you multiply it by any other matrix, you get that matrix back again. And we have inverses because we only looked at invertible matrices. Invertible matrices are invertible because if they weren't invertible, we didn't put them in this collection. So that's what GLNR is. That's an example of an infinite group. And it's not commutative because AB is not the same as BA necessarily. We can come up with other general linear groups by changing the entries. Instead of the real numbers, we can put other things. For example, GLNQ is group of invertible n by n matrices with rational entries. We will get, with the same proof as before, that we have a group. If you have the entries be complex numbers, GLNC will be the group of invertible n by n matrices with complex entries, and that's an example of a group. Or if P is a prime and you look at integers mod P, then you can have those to be the entries of your matrix. And this will be a finite group. You will not have infinite number of elements because there's only finite number of possibilities for the entries. So these are n by n invertible matrices with entries being 0 through P minus 1. And instead of the cumbersome GLN comma z mod pz, we write glnp for that. The real numbers, the rational numbers, the complex numbers, and z mod pz are examples of fields. And there's plenty more fields out there, and we will study them in field theory. For now, we just want to focus on these four. In general, if f is any field, and I'll tell you what that is, even though I don't really want to focus on that too much at this point, then the group GLNF is the group of n by n invertible matrices with entries from that field. So in general, you can have any field. What is a field? So F is a set. It has two operations, plus and multiplication. And assume that with plus, you have closure, you have associativity, you have commutativity, and you have an identity, which we call 0. And every element has an additive inverse. In other words, with plus, you have a commutative group. And also with multiplication, as long as you throw away 0, you again have closure, you have associativity, community, and you have an identity. This time that's called 1. And every non-zero element has an inverse. So again, after throwing 0, you also want a commutative group. And also you have to have distributive laws that connect the addition and multiplication. Then we say that this is a field. Again, fields are things that we will study in detail in lectures on field theory. But for now, any place where you can do all four operations, if you can add, subtract, multiply, and divide by non-zero elements, that's called a field. You have all four arithmetic operations. And those guys can be the entries in your matrices. So Q, R, C are fields. The integers is not a field because you can't divide integers. And Z mod PZ where P is a prime is a field. That's a finite field. Those are not the only finite fields. There's also finite fields of order a power of a prime, but those are a little bit more complicated to think about, and we will do so in the field theory lectures. If F is a field, then the general linear group, I'm repeating myself, GLNF, is the group of n by n invertible matrices with entries in F. And instead of GLNZPZ, we just write GLNP. That's the notation. If this is your first time through abstract algebra, then whenever you hear the word field, just think the real numbers, the complex numbers, the rationals, or integers mod P. That's all I want you to do. If you already know about fields, then the entries could be from any general field. For example, they could be rational functions. As an aside, in a general vector space, you decide what the scalars are. You don't have complete freedom. You have to pick a field for your scalars. Usually in a first time through linear algebra, the field is the real numbers. The scalars are real numbers, but they can be complex numbers. That's very useful. For example, in physics, they can be rational numbers, and they can be from Z mod PZ or any general field, if you know what that is. What is SLNF? If F is a field, then it has a multiplicative identity, 1. It has a 1, something that when you multiply, nothing happens. GLNF is the general linear group. Then SLNF is going to be all those invertible matrices whose determinant is 1. That's called the special linear group over F. When we say over F, that means that the entries are from F. So the special linear group over F is those elements of the general linear group over F that have determinant 1. For example, if P is 2, then GL22 consists of these 6 matrices. These are 6 2x2 matrices with entries from Z mod 2Z. In fact, SL22 is the same as GL22 because in GL22, when P is 2, the only numbers are 0 and 1. So the only possibilities for the determinant are either 0 or 1. The ones who have determinant 0 are not invertible, so they're not in GL22. The ones that have determinant 1 are in GL22, but then their determinant is 1, and so they're also in SL22. So this is true for SLN2 is the same as GLN2. What's the size of GLNP? GLNR is an infinite group. GLNQ or GLNC are infinite groups. If you have an n by n matrix with entries from complex numbers, you can get an infinite number of them. But if the entries come from Z mod PZ, then that's a finite group. There's only a finite number of matrices, and I want to know how many of them are there. Well, Z mod PZ itself, the entries, are 0 through p minus 1. If you don't know what that is, watch my videos on Z mod NZ. Now, if in any positive integer, I want to know how many elements are in GLNP, invertible n by n matrices with entries from Z mod PZ. How am I going to come up with how many of them? I'm going to just construct all of them, and I'm going to count as I go along. The way I'm going to write down an n by n invertible matrices is that I'm going to write them row at a time. So I write the first row, then the second row, then the third row, and I go down. I'm going to make sure that the first row is not a row of zeros. I don't want that, because if you have a row of zeros, well, the matrix will not be invertible. And then after that, I just make sure that each new row is not a linear combination of the ones before that. Why does this work? Because of two facts from linear algebra, both of which are in videos that I have on linear algebra. In the notes somewhere gives you a link to them. First, a matrix is invertible if and only if its rows are linearly independent. That's a fact from linear algebra. And the second fact is that if you start with an ordered finite set of vectors, if you have a set of vectors, like for example, the rows of this matrix, and they're ordered, you put them in order, the first row, second row, third row, and so on, to see if it's linearly independent or not, what you have to do is check two things. Is the first one the zero vector or not? For the rest of them, is any one of them a linear combination of the ones before? If the first one is zero, if any one of them is a linear combination of the ones before, then that set of vectors is linearly dependent. But if the answer is that none of them is a linear combination of the ones before, and the first one, which doesn't have anything before it, is not the zero vector, then the whole set will be linearly independent. Given those two facts, if I construct a matrix by making sure that the first row is not the zero vector and everyone after that is not a linear combination of the ones before, I'm assured to get invertible matrix. And in fact, I will get all invertible n by n matrices that way. Now let's go ahead and count the number of elements in GLNP. For the first row, how many choices do I have? Well, I have n entries. For that first entry, I have p choices because I can pick anything from 0 through p minus 1, z mod pz. And I have another p choices for the second entry, another p choices, and so forth. So I have p to the n choices. But there's one choice I can't have, and that's all zeros. So for the first row, I have p to the n minus 1 choices. Now, what about the second row? Well, again, I have p to the n choices, but I can't pick all of them because some of them are a linear combination of the row that I just wrote. How many of those are there? Well, the row I just wrote, whatever it is, has how many linear combinations of it? Well, it's just one row. So how many times can you multiply that by a scalar? Well, there's p scalars, 0, 1, 2, through p minus 1. Those p scalars, every one of them that you multiply by that row gives you one of those rows that I'm not allowed to have. So there's p rows that I'm not allowed to have. By the way, if you multiply by 0, you get all zeros. I'm not allowed to have that. If you multiply by 1, you get actually that first row. You're not allowed to have that. Twice that, you're not allowed to have. 3 times that, p minus 1 times that, you're not allowed to have. But anything else is not going to be a linear combination of those. So for the second row, I have p to the n minus p. P to the n is the total number of vectors of length n that I could write. P of those are a linear combination of the row before. So pn minus p is how many things I can put there. What about the third row? Now, the third row, again, I have p to the n choices, but I can't write any of the linear combination of the first two. So how many linear combinations of the first two rows there are? Well, I can multiply the first row by one scalar and the second row by a different scalar or the same scalar. And I have p choices for that first scalar and p choices for that second scalar. That's p times p squared ways that I can make a linear combination of that first two rows. And those are the no-nos. Those are the ones that I'm not allowed to have. So for the third row, I have p to the n minus p squared choices. And this continues like this. Now I have the theorem that if n is a positive integer and p is a prime, then the size of GLNP, the number of n by n invertible matrices with entries in Z mod PZ, is Pn minus 1 times Pn minus p times Pn minus p squared, and so forth. Because Pn minus 1 is how many choices I have for the first row. Regardless of which one I pick, I have Pn minus p choices for the second row. Regardless of which one I pick, I have Pn minus p squared choices for the third row. Regardless of which one I pick, I have Pn minus p cubed choices for the fourth row, and so forth. So that's the size of the general linear group GLNP. And what about the size of SLNP, the special linear group? The special linear group is those matrices in GLNF, those invertible n by n matrices whose determinant is 1. Pick a prime and pick the size of your matrices. When we put absolute value signs around a set, we mean the size of that set or the cardinality of that set if it happens to be infinite. Then size of SLNP is just the same as the size of GLNP divided by p minus 1. Why is that? So here I'm going to sketch the proof. I'm not going to put in all the details, but you can complete it. If A is an invertible n by n matrix with entries from Z mod PZ, where P is a prime, then its determinant can be 1, 2, 3, all the way till P minus 1. It can't be 0 because determinant 0 corresponds exactly to those matrices that are not invertible. In GLNP, we're looking only at invertible matrices whose determinant is not 0. What this means is that there's P minus 1 choices for the determinant. And what is true is that they occur uniformly, that there's as many matrices whose determinant is 2 as there are matrices whose determinant is 5. Because of that, they are distributed evenly because there's p minus 1 choices. 1 over p minus 1 of elements of GLNP have determinant 1. Why are the determinants distributed evenly? If there's justice in the world, why would there be different number of matrices whose determinant is 2 versus the number of matrices whose determinant is 5? There just doesn't seem to be any good reason why that would be. So intuitively, it does make sense, but that's not a proof. I'm going to sketch the proof here. Pick alpha and beta to be non-zero elements of Z mod PZ. So these are the two possible determinant values that we want to show that there's as many matrices with determinant alpha as there are matrices with determinant beta. Let S1 be those elements of GLNP, those invertible n by n matrices over Z mod PZ whose determinant is alpha, and S2 be those whose determinant is beta. And what we want to show is that the size of S1 is the same as the size of S2. The way we are going to do that is by focusing on this matrix A, which is a diagonal matrix. It's a matrix that on the top left corner, it has beta over alpha. Beta and alpha are elements in Z mod PZ, and Z mod PZ is a field, and therefore you take beta and divide it by alpha and get an element of Z mod PZ. And everywhere else is ones. That diagonal is mostly ones, except for this one entry that's different. Now, this matrix A, it's determinant beta for alpha because it's a diagonal matrix, so it's just a product of diagonal elements, and it's invertible because its determinant is not 0 because beta was not 0. Then you're going to define a function from S1 to S2. One way to show that two sets have the same size is to give a bijection, a one-to-one correspondence between two sets, to say that this element of this set and that element of that set correspond to each other. And we're going to define that by f of n equals an. If a matrix n walks through the door from S1, you pre-multiply it by A, and you will get A times n. And the determinant of that is going to be beta. Why? Because the determinant of A is beta over alpha, determinant of n is alpha, and determinant of an is the same as determinant of A times determinant of n. So this does give you a matrix in S2. So I will leave it to you to show that this is well defined. I actually just gave you the argument for why it's well defined, but it's also one-to-one and onto, and that is because A is an invertible matrix. So you have a bijection, and that bijection then proves that the size of S1 equals the size of S2, and so the proof is complete. We showed that all determinants are distributed evenly. For invertible matrices, there's p minus 1 choices, so the size of SLNP is 1 over p minus 1 times the size of GLNP. I want to finish by talking about linear transformations. Why is GLNF called the general linear group? Let's focus on GL2R, 2 by 2 invertible matrices over R. When we write over R, we mean the entries are from R. And these correspond to invertible linear transformations from R2 to R2. You have to fix a basis. As soon as you fix a basis for R2 and use that basis for the domain and the codomain, then every invertible linear transformation gives you an invertible matrix, and every 2 by 2 invertible matrix gives you an invertible linear transformation. For a fixed basis, there's a one-to-one correspondence between 2 by 2 invertible matrices and invertible linear transformations from R2 to R2. So this is where the word linear comes, because these correspond to linear transformations. Now, where does the word general come? Linear transformations don't have to be invertible. But if they are invertible, then they have the property that, for example, in R2, if you take 3 points in general position, 3 points in general position means 3 points that are not all on the same line. Then if you take their image, if the linear transformation is invertible, then you're guaranteed that the image will also be in general position. If it wasn't invertible, it's possible that those 3 points will collapse all into one line. And so 3 points in general position may transform to 3 points not in general position. But if you have invertible matrices, that doesn't happen. I have a whole set of videos on linear transformations and their relationship with matrices in my linear algebra videos. You're welcome to watch those for more detail. We can do this more generally if F is a field and V is Fn, a vector space of dimension n over F. When we say over F in a vector space context, we mean that the scalars are from the field F. Then GLNF, well, we know what that is. It's n by n invertible matrices with entries from F, but that corresponds to, that's the same as all the invertible linear transformations from Fn to Fn. Again, you have to fix a basis first for Fn. You can think of these objects as n by n invertible matrices or invertible linear transformations from Fn to Fn. You can also denote this by GLV, V being that vector space. And if you do that, you can actually even let V be an infinite dimensional vector space. That doesn't correspond to matrices anymore. So it's actually more general. It's more general to think about linear transformations and not think about matrices. For our purposes, thinking about matrices makes calculations and thinking about things a lot easier. Matrix groups, that's a vocabulary that you might run into, are subgroups of GLNF. If you pick a bunch of invertible matrices and they form a group, that's a subgroup. A group within a group is called a subgroup, and those are called matrix groups. Any group that's isomorphic to a subgroup of GLV is called a linear group. Two groups are isomorphic if you can relabel the elements of one. Then when you look at the multiplication table of the two, they look identical. Those two groups, as far as group theory is concerned, are going to be the same, and we use a fancier word, isomorphic, for that. So basically, subgroups of GLV are linear groups. Now, linear groups and matrix groups are basically the same as long as V is a finite dimensional vector space. If V is infinite dimensional, then there are linear groups that are not matrix groups. This is the end of this lecture. This was the last video to give you examples of groups. There was on symmetries of square, permutations of a set, Z mod NZ, the group of units of that, and this was one on GLNF. We are now going to have a whole long list of videos on the theory of abstract groups. When that's done, there will be a video on why we should study rings, and then we will dive into theory of commutative rings, and if there's time left and energy left, there will be also a set of videos at some point on fields and Galois theory. This is the end of this lecture. Keep hydrated, mind the gap, and like and subscribe to my videos. Like my videos if you like them, subscribe to them if you like to be subjected to math videos in your feed. I will see you in the next lecture.